Morning, sir.
Good morning. How are you today?
Cold.
Okay, but surviving.
I'm surviving.
Okay.
I'm arguing with my cases in this program. I thought I had it, and then I realized my cases were not as good as they should be.
Which program?
The homework number 4.
Okay. I have many people who submitted this homework.
Well, I have, because my cases are wrong.
Okay. Have you all finished our program that I gave you about the bouncing switch?
I have not.
Jose?
No, I'm still working on it, Professor.
Sorry, I have to continue. And of course, I cannot keep the rest waiting for somebody to finish.
Professor, I have a question.
Okay.
It says there's a quiz that opens up tomorrow.
I am not asking about you, but we are going to use it over and over. So you will miss it.
Is there a quiz due soon?
Yes, there is a quiz tomorrow.
Okay. But there's nothing else besides that quiz, right?
Yes, quiz, all day quiz.
Okay, got it. Thank you, Professor.
But the lab is still going on, correct?
No,
Ah, thank you.
quiz only. Okay. Today we are going to start.
Let me interrupt.
Pardon me?
This is Ballard. So when we come in at 7 in the morning and start, you'll have the quiz there for us?
The quiz will be the same as last time. Do you remember quiz 1?
Yeah, but it wasn't on a lab day.
It doesn't matter. It is going to be online.
Okay, at 7 o'clock in the morning. Thank you.
It will be released from your announcement at 7 o'clock. You finish, upload. That's it.
Okay.
Same as last time. Clock domains. As we can see here in this slide, I have my processor. It is working at a very high speed. 528 megahertz. This is the clock of my processor. But the memory is a little bit slower, 132 megahertz. I have many peripherals connected and communicating with the processor at different speed. So I have here in between the memory and the processor, this line, it is called clock domain crossing. I have to get or to invent a device that would make both the processor and memory speak to each other while they are operating at different frequency. If that is not provided, I will get a metastability problem. What is the metastability? It arises when you have two domains at different clocks. And the metastability, it is, I am transferring, for example, 1 that is high or 0 that is low. Since we have different clocks, I may not reach, the one may not reach the receiving end as 1. it could be anything in between. It can be 0, it can be 0.2, it can be 0.5, anything in between, or it can be 0 or 1. So we call this a metastability. And of course, we need to avoid that by observing the setup and hold time. To remind you about setup and hold time, this is my clock. And for my signal, this is my signal. My green signal must be available before the arrival of the rising edge. This is called setup time. As you can see here, the green and the blue are starting almost at the same time. So we haven't observed the setup time. And here, for this clock, the green went down very fast. So it will never catch the clock number 4. So I need to observe, this is called the hold time. So my signal should start before the rising edge by the setup time and remain as is, high or low, after the rising edge by the hold time. This is to avoid the metastability issue. So, as I said, it can be 0 or 1 or anything in between, but anyway, the data will be invalid during this metastability period. And sometimes it may oscillate between 0 and 1. Again, this is another version of corrupted data. Those are examples of metastability. Suppose that we have a state machine. This state machine, this is my state and this is my next state. And I have here, D is my input. It is operating at clock 1. And the state register is operating at clock 2. Now my next state will be fed from clock 1. D will come at a speed. And the state register is operating at different speed. This may cause a metastability. For this one, I have memory. I am feeding the memory from this D flip-flop, but they are operating at different clocks. So the data, again, might be corrupted. This 2 D flip-flops. Flip-flop 1 will operate and reset the second one. But here, as you can see, the first one is operating at clock 1. So the reset will occur at clock 1, while this D flip-flop is operating at clock 2. This is the last one. It is another version. I have this data coming in through D flip-flop operating at clock 1. And this is my clock 2 operating to feed D, the second flip-flop. So while those are cascaded, but they are at different frequencies. So I expect different data from the input data. Let's see it in this time diagram. This is the data coming in. This is the first clock, A clock, which is this one. And this is the A data out. A data out, this is my data in. A data, this is my input data. A clock here, and this is my A data, the output at this point. Now, this A data is feeding what? It is feeding the second flip-flop, which is operating at this clock. This is my A clock, and this is my B clock. Page?
Yes.
Which is faster, A clock or B clock?
A clock.
A clock is faster. So this is my data, A data that is feeding the second flip-flop. Now, this clock here of B, it can see what? It can see 0. So, okay, 0, no problem. The second clock, what does it see? It is seeing this A data transiting from high to low. This data didn't meet the setup and hold time. So I will get a metastability case. Instead of having a definite high or low, I am getting a metastability case. For this clock, now I have A data 0. So I will get out 0. But this A data that came in and went away, it wasn't properly caught by the second flip-flop, and it generated a metastable data. We will need a synchronizer circuit that will look at the both frequencies and make a matching and guarantee that we don't go into a metastability. One type of synchronizer, it is called two flip-flop synchronizer. I have this, my first one. This is data, and it's working at A clock. And this is A data out. Let's trace this one and see it. This is my A clock. And this is my A data. At the rising edge, A data, the output here went high. And at the rising edge here, A data went low. So this is my A data. BQ2 should look the same as this one. It can be slower, it may come later, but I need to see this is coming out. How does this circuit differ from the previous one? Here I have A data, and this is B data. I have only one flip-flop. But for this one, I have two flip-flop. And those two are operating at the second clock, the B clock. Let's see how this will affect the performance. With one flip-flop, I got this metastability from the first from this BD flip-flop. I expect to get the same thing from here. So BQ1 will be this metastable case. But let's look at the second flip-flop. The second flip-flop will take this metastable data and will catch the high of it and reflect it to its output. In this case, you can see it is going to go high, and with the next B clock, it will go low because I have here 0. If I look at this one and this one, A data and BQ2, you can see they are similar. Both of them are high for 1 clock cycle. This is high for 1 clock cycle of A, and this is high for 1 clock cycle of the B clock. So the second flip-flop managed to remedy this effect. And with 2 D flip-flops, I have a correct data.
Professor, I have a question.
Yes, sir.
Okay, so BQ1 data is the input for the second flip-flop in the synchronizer in
Yes.
order for us to get the correct BQ data out, right?
Yes.
So how can BQ1 data even trigger the output if it's basically in between the required one-shot trigger, like voltage threshold? Like you see how it's like a weird signal?
If we know that high is considered not 5, it can go down up to maybe 2.2 or 2.3 volt.
Really?
Low, it is not just 0. 0.6, 0.7, maybe 0.8 could be considered 0. So
Wow.
in this case, we are lucky enough to have this, but this is not my best option.
Oh, I see. So with
This
this
is
kind
not
of
my best option. I
So the
have many
Mhm.
more techniques, but this
Okay.
is one of them. This is the simplest one.
I see. So
Okay.
for would I be able to find that information in a data sheet, say for like a processor of some sort,
Which data?
or maybe not a processor, but in the data sheet, basically the voltage thresholds for triggering the clock?
Oh, yes, it is in the data sheet. For example, the TTL 7400.
Okay,
If you go to the data sheet, you are going to find the setup time and the hold time for it.
I see. But also like the minimum threshold to trigger a high response. So for example,
You are
like you
going to
said,
find
down
yes,
to,
yes.
wow, that's a lot. Thank you.
In Digital One, we used to have it as one of the experiments. We used to experiment it. Okay. This is the same technique that we spoke about, the same technique. Here I have, you can see, this is my A data. It came in and it came out. And this is my B clock. This is my B clock here, and this is my A data. At this time, when I got the rising edge, Jose?
Yes, Professor.
For this one, I have here, what is the value here? Of
0.
A data? 0. And this is my rising edge.
Yes.
So what will be this BQ1? I inputted here 0. What will be the output here?
So if it's 0,
0, another 0. At this
Uh-huh.
rising edge, I will have 0.
Right.
And since BQ2 hasn't received anything, it will continue to be 0. Now, with this rising edge of a clock, are you still with me, Jose?
yes, yes, I'm here.
It found out that I have a 0, so my A data went to 0.
Right.
Now, with my rising edge of B clock, what can we see?
So the B clock is rising.
B clock here,
is
rising,
one.
and it will check here. What will it
Right.
find?
0.
So it will continue 0, and B, of course, will continue 0. A data, we don't have any more data coming out. So this A data came in and vanished, and the BQ1 and BQ2 couldn't catch it, correct? You can see here high and low, but BQ1 and BQ2 is always 0. Nothing happened over here. Why is that? Because the A data was very short. We need to ensure reliable operation, A data to last at least 3 clock cycles, 3 clock edges. Okay? But for this one, this is a very bad design because I have here my data is very short compared to the clock cycles, the clock speed. Let's try to correct this. Can you see here? I have here, this is my pulse A data. It is quite long. At the rising edge, I am high. Another rising edge, still high. Third rising edge, high. Fourth rising edge, it is low. Now, let's go and see what is happening over here. Vitaly?
Yes, Professor.
Vitaly,
Yes, yes,
this is my B clock,
correct.
but this A data here is not early enough. So this BQ1, it is a metastable. Can you see it?
What do you mean A data is not early enough?
This
It looks,
it looks a little bit before, but not before enough. I need more time.
I see. Not enough hold time,
Yes, not
rise time?
setup time.
setup time, sorry, yes, gotcha. Okay, so you have like a little bit of noise basically from the signal.
This is the beta stable.
Okay,
Now, for the second B clock,
mhm,
can you see? This is high before
Mhm.
the rising edge of the B
okay,
for a long time, and it will remain high for a long time after the rising edge of B. This is
perfect.
setup
So-
time. This
so the
is my
threshold
hold
is one.
time. Both of them are satisfied here.
Yes,
So I will get a very nice and clean high signal.
but part of the signal is missing, right? Because it's not as long.
We cannot say it is missing. I got it here and it is correct.
I see.
It is
But
late, but this is the correct one. And wait a moment. What about the second D flip-flop? The second D flip-flop, what will it see?
The second B flip-flop is going to see the B data 1 input.
Yes, it's gonna see here. This is the clock here. This is high before, well before the clock. And I'm gonna get a very clean high. So extending the pulse width to cover 3 clock cycles guarantees
Cloud over here in electrical.
that this output PQ2, not PQ1. It is the correct one. Yes, it is delayed from A data, but here I am just synchronizing.
Mhm.
I am not matching the speed. I need just synchronize between the 2 speeds and transmit the same A data will be transferred to the BQ2.
So I have 2 questions.
Yes,
Okay, so basically BQ1, it kind of just acts as like a signal for getting the desired output at a switched frequency for BQ2.
yeah, BQ1 is taking, it can be in a metastable operation, and it will get you the correct data, but after a while, BQ2 will never see any metastable. Why? Because BQ1 and BQ2 are working at the same clock.
I see. So AQ1, or sorry, A data 1 is the initial input signal at a specific frequency. And as
Yes.
long as we see the scaled down, the desired response at a scaled down frequency in BQ2, we're happy.
Yes, correct.
Okay, perfect. And my second question, I noticed in one of the earlier examples, it kind of looks like if this is to scale, A clock is at a higher frequency than B clock, right?
Yes, it is.
So wouldn't we expect, maybe this, I'm asking if this matters or not, but you see how A data is kind of a long pulse compared
Yeah.
to B data 2, it looks like a smaller pulse. Wouldn't this, like, I mean, if this is like serial data transfer of some sort, and that's information stored, aren't we losing information if the pulse is shortened and it's not adjusted for the frequency?
This case here,
Yes. So
we lost the data. We
the one
lost the
before,
data.
I think in the one before.
This
Right,
one,
so
we got
so-
the data,
Right. So A data 1.
but not very reliable.
Right, I know it's not reliable, but I'm just asking like the actual length of the signal, the data. It looks a little bit longer here.
I
for
am
B data
sending
2.
you at a very high speed, 101.
Okay.
Since I am passing by 2 D flip-flops and a very slow clock, you are going to receive 101, but at much
At a-
lower speed.
Okay. So you're still getting all the data, just at a different time.
Yes, you are going to get the data.
That was just my question. I wanted to make sure all the data was passed through. That makes
No,
sense. now.
we are transferring or exchanging the same data, but at different speeds. This is called synchronizer.
Perfect. Makes sense.
So then, Professor, I had a question on that BQ1. If you went back to the slide we were just talking about for a while, no, the most recent slide.
Yeah.
Yes. So that little bump on BQ1 is due to the not having enough setup time. Is that
Yes,
correct?
correct.
Okay. Thank you.
Can you see here? You see this black area?
Yes.
This is the setup time. I have to have my data before this setup time. Can you see A data? It is
Yes.
high, long before the rising edge, much longer than the setup time. And this A data, it remained high, well beyond the hold time. This is my hold.
Okay. That makes sense. And so even
If you may recall, when you are using the waveform generator, when you start running the simulation, you have two options. One option is logic. That is what you are using all the time. Another option, it is time. In this time, you are gonna see a problem like this happening. If the setup time is not met or the hold time is not met, you may not get the correct output. If you have many cascaded D flip-flops, counters, clocks, all of those are cascading. So there is a propagation of delay. This may cause a problem to you. That is why we use, after we are happy with the logic simulation, we do another time simulation before putting this product into my FPGA kit and before putting it into the market, of course.
Can you go back one slide? I'd like to ask a question.
This slide,
That, no, forward one,
one before,
forward, not back. That, okay, the pulse not formed there. That was a low, but what if that pulse had been high enough to actually make a one come out? Right
this
there.
one?
Yeah, on BQ2, no, in other words, the pulse,
You mean at this area?
no, right where the highest pulse, the highest point was and where it says there.
This
What
one,
if that
This
went
one.
high enough?
this one.
Yeah,
The problem with this one, it is high now, but it hasn't met the setup time. This is the setup time. It should be high here. At this point, it should be high, and it should remain high up to here. Yes, it is high here, but it's not early enough.
so it would never bounce high enough so that
This
BQ2 would
For
be,
this one, as I said, it started, it saw this high, but it didn't have enough time. If I have this A data way back to the left, this one would have been correct.
okay,
But it happened that this is my B clock rising, and this is just before it. It didn't meet the setup time. It meets the whole time, but it didn't meet the setup time. That's why I get this bounce. And of course, this bouncing or this jump, now I have this clock coming while I have a very stable long pulse, so I caught it. And this will be reflected on the next clock pulse to the output. So this B output is crystal clear and clean from any bouncing.
got it.
Hello, Chad? Hello, Chad?
Yes, Professor.
Can you see this slide?
Yes.
This is another form of synchronizer, the switch debouncer.
Okay.
That's why I asked you at the very beginning, have you finished this? Because it is here. And many things will be built on it.
Okay.
So this has the same technique. I have here an oscillation with my push button, and I manage it to have 2D flip-flops, and I am comparing them, as we said last time, by XOR, and I guaranteed that they are equal for long time by using the N counter. After they are quite stable and equal for long enough time, I will enable the output to read the data in and send it to the output. This is another version of synchronization. This one and this one are called open loop. Open loop. This open loop is very simple, very fast, but it has the disadvantage that there might be a problem when there is a change in the structure of my design. For example, if my design requires that I change the clock, this open loop will not fit. It may get still metastable. Suppose that I am getting data, fast data, not with enough long duration. I will get another metastable condition. This takes us to what is called closed loop. This closed loop, it is a very reliable handshaking synchronizer. To understand this, can you see this dotted line? I have here 3D flip-flops, and all those three are operating at a clock. Here, this dotted square, I have 2D flip-flops, and those 2D flip-flops are operating at B clock. I am gonna give you 5 minutes to track down the A data. Can you see how I'm traveling? Until you get AQ2. Please track it, take 5 minutes, and try to see the timing diagram below and understand what's going on before we speak about it. Hello, guys.
Yes, Professor.
Samuel? Hello, Samuel?
Hello?
Are you ready?
Am I ready?
Okay. Now, let's go one step at a time. This is my A data and this is my A clock. What will be A data 1? This is my A data. And this is my A data 1. Let's see how we got it. This is my A clock, it is high. And A data wasn't there before the clock with the setup time. So A data continued on 0. At the second clock, Samuel, do we have A data available?
Yes.
And it is available. And it has been here before the setup time. And it will continue after the whole time. So I expect, can you see A data 1 going high? Very stable operation. And this A data, please track it. 1 clock cycle, second, 3, 4. On the 5th one, A data is going low. But this clock cycle didn't catch it, so it still thinks it is high. But on the following clock cycle, it is very stable 0. That is why I got this A data to be 0. Clear, Samuel?
Yes, that's clear.
Okay. Jose? Hello, Jose?
Yes,
Are you
Professor.
available? Jose?
Yes.
Can you see here, I have, this is my A data 1. It is going into BQ1.
Yes.
And BQ1 is operating at B clock. So
Correct.
this is my A data, and it is going to BQ1 through this clock. Now let's see what is happening to BQ1, the output. This is my clock, and the data is available before the clock by the whole time, and it is available after it by, sorry, before it by the setup time and after it by the whole time. So I will get this one. So I have here a very nice B data. And this is my A data 1 available all of that time. So I have this available all of that time. Now I have 0 at this clock. I will go to 0. Clear?
Clear.
Page? Hello, Page?
Hello? It's
This
making
is-
sense. It's a little slow for me.
This is BQ1, and it is operating at B clock. This is the input of this second B flip-flop. This is the data input, and it is working at the B clock data. Here, I didn't catch this BQ1, but here I can catch it very well. So it will go high, all of this high. It didn't catch it as it's low with this rising edge, so it will continue to the next one. Is this clear, BQ2?
Yes, it is. It's just a lot to process when there's a bunch of flip-flops going on, but if I step it through like that, that makes sense.
Yep. Now, Jim. Hello, Jim.
I'm here.
Can you see this BQ2? Where is
Yes.
it going?
And it's going back to the old time clock.
Yes, to AQ1. So this one, now it is operating at this clock to generate EQ1.
So it went
here-
high there.
Yes, it went high because I have a rising edge now, and this rising edge met AQ1, so I have high. And this AQ1 is feeding AQ2, as you can see it.
Professor, I have a question.
Yes,
So
sir.
at the next clock, and the next clock cycle, the second one, AQ2 went high and stayed at the same, it stayed high, the same length, but one pulse behind.
Okay, that's correct. That's correct. Before
Professor,
you ask Vitaly,
Okay.
this is my very input A data in here. And this is my last output, AQ2. I went through all of these process and I got it from the circuit B and synchronize it back to AQ2. Yes, Vitaly.
So if our initial input was A data and our final output is AQ2 data,
Yes.
why was it even required to transition to a different clock frequency on the BQ data side and then revert it back to the A clock side just to get the same clock output? I mean, what was all that for? Couldn't we just make a simpler flip-flop circuit?
As you can see, what are the disadvantages of this circuit? I have so many flip-flops, as you can see, and I have a lot of delay because of passing through all of this. But here, I am guaranteed that this data is the same. Yes, this as it is, if I can get the output at different rate, yes, that I can take here, BQ2, for example. If I take BQ2, it will be okay, no problem. But I am getting the same data, but at a lower rate. I needed to lower AQ2. I didn't want it to be as fast as A data. You can see here after 3 clock cycle, I started after 4 clock cycle, I got AQ2. So I lowered the speed. I wanted to move from high speed to a lower speed. So AQ2 came out, but it came after 4 clock cycles.
I see. That makes sense.
Okay.
And I agree. The closed loop is definitely the safest, most reliable control. So
Yep.
that
Should
makes
be.
perfect sense. Thank you, sir.
We are gonna stop here, and tomorrow I wish you the best during your quiz. and we'll continue on this on Wednesday. Any questions?
Are you going to be present for the quiz tomorrow on Zoom
No,
or
no,
not?
no.
Oh, okay, thank you.
Okay. Any assumption you need, just do it.
Paige, are you on campus?
No, I'm not.
Would you text or email me, please?
Yep, sounds good.
Okay, thank you.
Okay, thank you all.
I'm also
Okay,
gonna be
now,
on campus at around like 2:30, if that would be easier.
That will be easier. Thank you.
Yep, for sure. See you then.
bye all.
Goodbye, doctor.
Bye.
Have a good flight home.
Thank you.
Thank
Bye-bye.
you.